number 3. A box of oranges. A box of oranges is inspected by examining 3 randomly selected oranges. Examining 3 randomly selected oranges. Randomly selected oranges drawn without replacement. Without replacement. If all the 3 oranges are good, the box is approved for sale. Otherwise it is rejected. Otherwise it is rejected. Find the probability that a box containing 15 oranges out of which 12 are good and 3 are bad ones. Bad ones, 3 are bad ones, will be approved for sale. Will be approved for sale. That is the problem. A box of oranges is inspected by examining 3 randomly picked up oranges are examined without replacement, drawn without replacement. That means one after other oranges are selected here and they are examined. If all the 3 oranges are good, the box is accepted for sale, otherwise it was not rejected. In such conditions, find the probability that a box containing 15 oranges out of which 12 are good and 3 are bad. 3 are rotten ones will be, rotten means bad oranges, rotten oranges will be approved for sale. Okay, once the box contains 12 good and 3 bad oranges, the probability that the box will be approved for sale. So box contains here 12 good plus 3 rotten. That means bad oranges. Once 15 oranges are in the box, if 3 oranges are drawn one after other without replacement, then let A, the first event is, if 3 are good, if 3 successively drawn oranges are good, then it was approved. Hence, let A be the event of getting of good orange in first draw. B stands for event of good orange in the second draw. C stands for event of good orange in the third draw. Let us suppose A, B, C. Here the 3 are drawn one after other without replacement. That is more important, without replacement. Now, happening of A intersection B intersection C. Once A intersection B intersection C is happened, the box is approved. Probability that the box is approved equal to probability of happening of A intersection B intersection C. Probability of happening of A intersection B intersection C itself. That is probability of getting good orange in the first attempt, in the first draw. That is probability of A into, once A has happened, the probability of B on the occurrence of A. That means in the first attempt, one good orange is drawn, and without replacement of that orange, again getting of a good orange in the second draw. And the third one is getting of good orange in the third attempt once A and B happened by multiplication rule of probability for 3 events. You can take like this. Now coming to probabilities. At first, getting of good orange out of total number of oranges is 12C1 by 15C1. The total number of oranges initially are 15. Out of 15, 1 can be selected in 15C1 ways. Out of 15, 12 are only good. So, probability of getting a good orange is 12C1 by 15C1. After happening of this, getting of again good. After happening of this, getting of good orange is 11C1 by, the number of oranges are reduced by 1 and the good orange is taken out. Hence, I am taking 11C1 by 14C1 to get one more good orange. Once AB happened, happening of C is 10C1 by 13C1 only. 10C1 by 13C1. So, the required probability that the box is approved once the 3 successively drawn oranges are good, then only it was approved. Hence, the probability here asked, find the probability that the box containing 15 oranges in which 12 are good and 3 are bad once will be approved. When did you say the box is approved? Once the inspected 3 oranges are good. Hence, the required probability is 12C1 is 12, 15C1 is 15 into 11C1 is 11, 14C1 is 14, 10C1 is 10 by 30. So, you can simplify this one, 5 2 ja, 5 3 ja. This is 2 7s, okay, which gives us 12 into 11 by 3 into 7 into 13. This is 22 and 13 by, still you can remove of course 4 times, it may take 4 times. So, 44 by, this is 91. The required probability that the box to be approved, is 44 by 91. 44 by 91. The required probability is 44 by 91. Such problems may be asked in the board. This is one important problem. Of course, based on these multiplication problems, multiplication rule of probability, the problems are very important. You have to make much practice on these problems. You may get a 6 marks problem on this probability. Problem number 4 of exercise 13.2. Exercise 13.2, problem number 4. A fair coin and an unbiased die or tossed. An unbiased, a fair coin and an unbiased die or tossed. Let A be the event. Head appears on the coin. Appears on coin. Head appears on coin. And B be the event. Three on the die. Getting of 3 on the die. Check whether A and B are independent events or not. Or independent events or not. A fair coin and an unbiased die or tossed. A stands for the event that head appears on the coin, and B stands for event of getting the number 3 on the rolled die. In such case, we have to check whether A and B are independent events or not. Okay. So here event A stands for okay. A fair coin is tossed. A fair coin is tossed. And A is event of getting head. A fair coin is tossed and A is event of getting head. Then yes, the sample space is here, getting of head or getting of tail, and A is getting of head. So therefore P of A is n of A by n of S. That is 1 by n of here n of S is 2 and n of A is 1. Hence probability of getting of head once a fair coin is tossed is 1 by 2. Next, an unbiased die. die is rolled, then sample space, in this case sample space is getting of 1, 2, 3, 4, 5, 6, and B is event of getting 3. So it contains only 3. So P of B is actually 1 by 6. N of B by N of S here, that is 1 by 6. Now we have to check whether A and B are independent. Now a fair coin and unbiased die is rolled. A fair coin and unbiased die. A die is rolled, of course. Tossed. The sample space is simultaneously the sample space equal to getting of head end 1 or getting of head end 2, like that, getting of head end 6 or getting of tail end 1, getting of tail end 2, and so on, getting of tail end 6. There are totally 12 possible outcomes here. Out of 12 possible outcomes, here A intersection B. A stands for getting of head and B stands for getting of the number 3. That is head, getting of head and 3. So that implies N of A intersection B is 1. So required probability of A intersection B is 1 by 12. Okay. But 1 by 12 is nothing but, this is 1 by 12 is the probability of A intersection B is here. Probability of A into probability of B. Because this is 1 by 2 into 1 by 6. You can say that probability of A intersection B is 1 by 2 into 1 by 6, which is P of A into P of B. Therefore, probability of A intersection B is PA into PB. Hence, AB are independent. Independent events. They are independent events. Once the probability of A intersection B is PA into PB, then AB are independent events. Here the both the events, defined events, are independent. If P of A intersection B is not equal to PA into PB, then they are dependent. If P of A intersection B is phi, then they are mutually exclusive. Mutually exclusive events, cannot be independent. Cannot be independent because the intersection probability is 0 in case of both the events are mutually exclusive. Next, fifth problem. A die marked 1, 2, 3 in red and 4, 5, 6 in green is tossed. Let A be the event the number is even. The number is even. And B is be the event the color is red. The number having, otherwise the number having red face. Otherwise the color is red. Or A and B independent, or A and B independent. Check whether A and B are independent, either independent or not. The faces of die are colored as the faces that was marked 1, 2, 3 is colored with red color, and the faces with numbers 4, 5, 6 are in green color. Such die is tossed once, and A stands for event of getting the number even number, and B stands for getting of red color face. Is either A and B are independent or not? That is the question here. So here A, event that the number is even. B stands for event of getting turning up of the face with red color. Event of turning up of red face. When a die marked 1, 2, 3 in red and 4, 5, 6 in green is tossed once. This is the data. Now probability of getting, straight away I am taking the probabilities. Probability of getting the number even number on the rolled die. Getting of even number on the rolled die means either getting 2 or 4 or 6. So 3 possibilities. The total number of possible outcomes are 6, either getting 1, 2, 3, 4, 5, 6. So this is 3 by 6. Since A contains 2, 4, 6. Okay. And probability of B. The probability of turning up of the face having color red. So 3 faces are in red color. Hence favorable possibilities to B or 3. The total number of faces is 6 here. So that is 1 by 6. Sorry, 3 by 6. 3 by 6. That is also 1 by 2. Either getting of green or getting of red. 2 ways. Either getting of red or green. Out of that, red is in favor. So hence 1 by 2. Either here the getting of red face and getting of green face are equally likely, hence it is 1 by 2. Now, probability. A intersection B is n of A intersection B by n of S. N of A intersection B. Happening of both A and B. Happening of both A and B is possible. in only one case, getting of the phase 2. So that is 1 by 6. Since A intersection B contains only 2. A intersection B contains only 2. The face having red color and which has an even number on that face. That is possible only 2. That is A intersection B. So n of A intersection B is 1. Total number of possible outcomes are 6. So 1 by 6. Here probability of A intersection B is oh wait. Here the probability of B. Here the probability of B is getting of red color. Red colors means out of 3 faces any one, getting of any one. Sorry, this is favorable possibilities is 1, 3C1 by 3. So 3C1 out of any one occur. 1 minute. 15, 12. Out of the faces, this is of course total faces are 6, and that is correct. Okay, that is correct. 1 by 2 itself. Okay. Total number of faces 6. Out of 6, and 3 are in favor of B. Okay. Now probability of A intersection B is not equal to probability of A into probability of B. Okay. Because this is 1 by 6, whereas the product is 1 by 2 into 1 by 2, 1 by 4. So therefore, A comma B are not independent. They are not independent events. Okay. The total number of faces either red or green is 6. Out of that, 3 are in favor of getting red. So that's correct. So here the given events are not independent, because probability of A intersection B is not equal to probability of A into probability of B. Okay. Next. Sixth problem. E and F be events such that let E and F be events with probabilities. Probability of E is 3 by 5 and probability of F is 3 by 10. And probability of E intersection F is 1 by 5. Or E and F independent. This is very simple problem. The probabilities are given here. 3 by 5 and probability of F is 3 by 10. Probability of E intersection F is 1 by 5, which is not equal to 3 by 5 into 3 by 10, which is not equal to 3 by 5 into 3 by 10 itself. So that is not equal to probability of E into probability of F. So E and F are not independent. Not independent. Okay. E and F are not independent. This is straight away problem. They are not independent. Next one. Problem number 7. Given A comma B are events with probability of A 1/2, probability of A union B is 3/5, probability of B is small p. Find P if they are mutually exclusive. The second case is independent. Okay. Once they are mutually exclusive, we have to find P. In another case, once they are independent, we have to find P. A, B are mutually exclusive. Implies, of course, implied probability of A intersection B is 0. Once A intersection B is 5 only, then they are said to be mutually exclusive. A, B are disjoint. There is no common possible outcomes to A and B. Then you can say that they are mutually exclusive. In such case, the probability is 0. That is, we know that, but to get this one, from addition theorem, of probability. Probability of A union B is PA plus PB minus P of A intersection B. Therefore, probability of A union B is given 3/5. P of A is given 1/2. P of B is P. Minus this is 0. Hence, P takes the value 3/5 minus 1/2. 3/5 minus 1/2. In such case, 3/5 minus 1/2. Otherwise, I will write here. So, therefore, probability of A union B is 3/5. Probability of A is 1/2. Probability of B is P minus probability of A intersection B. Once they are mutually exclusive, 0. So, P takes the value in this case 3/5 minus 1/2. 10 is our LCM. So, 6 minus 5, 1/10. In this case, the probability of B, happening of B is 1/10. The second one, independent case. If A, B are independent, then that implies and implied probability of A intersection B is PA into PB. Probability of A intersection B is PA into PB. So, by addition theorem, probability of A union B equal to PA plus PB minus P of A intersection B implies this is 3/5 equal to 1/2 plus P minus 1/2 into P, because this is the product of P of A into P of B. From this 3 by 5 plus 1 by 2, 3 by 5 equal to 1 by 2 plus p by 2, because p minus p by 2 gives us p by 2. Hence p by 2 is 3 by 5 minus 1 by 2, which is 1 by 10. Therefore, in this case p is 1 by 5. Mutually exclusiveness of events does not mean that they are independent. Mutually exclusive property is the property of the disjoint subsets of sample space. So they belongs to same sample space. A and B or belongs to same sample space. Then you can say whether they may be mutually exclusive or not. But whereas for independent events, both A and B need not belongs to the same sample space. They may be belongs to in different sample spaces. So mutually exclusive need not be same to that of independency of the events. This is in mutually exclusive events, there is no common possible outcome to A and B in mutually exclusive events. In independent events, there may be a possibility of having common possible outcomes to A and B. So these are all the different properties of mutually exclusive and independent events. So once they are mutually exclusive, they cannot be independent. Note point. If A and B are two non-impossible events, then if A, B are mutually exclusive, impossible events and mutually exclusive, they cannot be independent. They cannot be independent. They may be independent, but once non-impossible events and independent, once they are independent, they cannot be mutually exclusive. Mutually exclusiveness need not implies independency of the events. Mutually exclusiveness belongs to same sample space, but independency of the events need not belongs to the same sample space. So these are all the differences between mutually exclusive events and independent events. Once the probability of happening of both A and B is 0, they are said to be mutually exclusive. Once the probability of happening of both the events A and B is the product of their individual probabilities, then they are independent events. Eighth one. Let A and B be independent events with probabilities P of A is 0.3, P of B is 0.4. Find first one, probability of A intersection B. Second one, probability of A union B. Third one, probability of A given B, conditional probability of A given B. Similarly, conditional probability of B given A. In case of independent events, once the probabilities of A and B are given as 0.3 and 0.4, you have to find these probabilities. So here A, B are independent, A comma B are independent. That implies and implied probability of A intersection B is always probability of A into probability of B. Okay. Now coming to first one. Probability of A intersection B is hence PA into PB is equal to P of A is 0.3, P of B is 0.4. This is 0.12. Probability of the combined happening of A and B is 0.12. The second case is probability of A union B. This is PA plus PB minus P of A intersection B by addition theorem. Addition theorem of probability. So this is PA plus PB. Since they are independent, intersection probability is product of the probabilities. Hence, probability of A union B is 0.3 plus 0.4 and 0.3 into 0.4 itself. This is 0.7 minus 0.12. This is 0.58. Again, the third case. Probability of A on the occurrence of B. By definition, this is probability of A intersection B by probability of B itself. The conditional probability of A on the occurrence of B. The conditional probability of A given B is probability of A intersection B by probability of B. This is probability of A into probability of B because they are independent by probability of B. So this is probability of A. B does not influence A here once they are independent. Hence, the conditional probability of A on the occurrence of B is probability of A itself. So that is 0.3 itself. Similarly, probability of B on the occurrence of A is simply P of B itself. In this case, PA cancel and we get PB, that is 0.4 itself. Like that you can able to find the required probabilities. Ninth and 10th are same models. Let us take 10th problem. 9th one and 10th one is same model. Of course, 11th is also same. If events A and B or events such that Probability of A is 1 by 2. Probability of B is 7 by 12. And probability of not A, not B is 1 by 4. State whether A and B are independent. If A and B are events such that P of A is 1 by 2, P of B is 7 by 12, and probability of not happening of A or not happening of B is 1 by 4, then check the independence of the A and B. So here P of A is 1 by 2, P of B is 7 by 12, and probability of not A or not B. Probability of not A or not B is probability of A complement. Not A means A complement, or stands for union. Not B means B complement. Okay, that is equal to 1 by 4. Probability of A complement union B complement is 1 by 4 implies this is probability of A intersection B whole complement is 1 by 4. Since A complement to union B complement is A intersection B whole complement. By set theory, A complement to union B complement is A intersection B whole complement. This is probability of A intersection B whole complement is 1 minus probability of A intersection B is 1 by 4. By definition of the probability of non-happening of A intersection B. So probability of A intersection B is here 1 minus 1 by 4, that is 3 by 4. Probability of happening of both A and B is 3 by 4. So here P of A into P of B is 1 by 2 into 7 by 12, that is 7 by 24. So probability of A intersection B is not equal to P of A into P of B. Therefore A comma B are not independent. So this is the conclusion. Not A or not B stands for probability of A complement union B complement. In case of not A and not B, you have to take intersection here. In such case, once you take whole complement, it becomes, once it is intersection, it becomes union. So like that, you can take the other problems, 9th and 11th same, and suppose in case of finding probability of A and B means intersection. In case of probability of A or B, that is union. Not A or B means probability of A complement or stands for union B. Like that you have to take the events and their corresponding probabilities. Next, let us take the problem 12th problem. A die is tossed. A die is tossed thrice. Find the probability of getting an odd number at least once. At least once. You have to find the probability of getting an odd number at least once. At least once means one or more times you have to get odd number. Okay. So a die is rolled, tossed thrice. A die is tossed thrice. Then the total number of possible outcomes are 6 into 6 into 6, 216. In each throw, the possible outcomes are 6. The first throw, you get 6 possible outcomes. In the second throw, 6 possible outcomes. Like that, in 3 throws, the total possible outcomes are 6 into 6 into 6, 6 cube, that is 216. Now probability of getting an odd number at least once equal to 1 minus probability of not getting an odd number. Not getting an odd number means getting of even numbers all the 3 times. Getting of even numbers. So getting of even numbers probability. Getting of even number probability means in the first throw you have to get even. That is possible either getting 2 or 4 or 6. Similarly in the second throw also either you get either 2, 4, 6, or in the third one also you may get either 2, 4, 6. So 3 possibilities. Hence the required favorable possibilities are 3 into 3 into 3 by n of s, 6 into 6 into 6, that is 216. That is 1 minus, this is 9 into 3, 27. So that gives us okay, which is 8 by 9. 8 by 9. The probability of getting an odd number at least once. Getting an odd number at least once is not getting 1 minus the probability of not getting odd numbers. Not getting odd numbers. Getting means even number in every attempt. Getting an even number in every attempt. So in first attempt getting of even number, that is possible one, the probability is 3 by 6. In second attempt getting of even number is 3 by 6. Therefore 3 by 6. Hence 1 by this is 9, 27. This is 8, not 9. So 7 by 8. Okay. 9 into 3, 27. 27 8s, 56, 12, 21. Okay. That is 7 by 8. Because they are independent events. Each attempt is an independent independent attempt, hence they are independent events, hence I am taking the product here, 3 by 6 into 3 by 6 into 3 by 6, hence we get 1 by 8 is the required probability of getting even number. So 1 minus that probability gives us the required probability.